All right, welcome back. So yeah, last time we finished up the graphics pipeline basics, although it was the whole graphics pipeline, and now we are on to frame buffers. So we've talked a lot about frame buffers in the past few chapters, and we've set up a render pass to expect a single frame buffer, which with the same format as the swap chain images, but we haven't actually created any yet. The attachments specified during the render pass creation are bound by wrapping them in a VK buffer object. The frame buffer object, references all of the VK image views that represent the attachments. Okay, cool. So attachments are referenced by VK images. Actually, they're represented by VK images, and the frame buffers reference those image views. Okay, in our case, that will be only a single one, the color attachment. However, the image that we have to use for the attachment depends on which image in the swap chain returns when we retrieve one for presentation. That means that we have to create a frame buffer for each image in the swap chain, right? Okay, and then we have to return the corresponding image to be drawn. Okay. To that end, create another vector or array class member that's going to hold our swap chain buffers or VK frame buffers. Okay, up the top we go, down here, VK frame buffer. Oh, god damn it, buffer. It's going to be that, an array of those guys. We'll create the objects. I'll turn your music down. Put this array in a new function called create frame buffers. That is called from within init Vulkan right after creating the graphics pipeline. Create graphics pipeline. Let's just copy that. Okay. And then create graphics. It would be good if Swiper would remember the last thing I searched for and I could just press up. I might have to code that in to Emacs. Okay, so down here, void takes in our app, point to the P app. All right, setup done. Start by resizing the container to hold all the frame buffers. Ooh, we don't need to do that. We just actually call malloc, don't we? Create our size. Okay, so it's the size of swap chain image views, which I think we already have in a struct member. Swap chain image count or something. Swap chain image count. Hello. Okay. So p app swap chain frame buffers is gonna be equal to VK frame buffer pointer, because it's an array of them, and we call malloc on that, and we say swap p app swap chain image count multiplied by size of our VK frame buffer. I think that's probably correct. All right. So there's our resize function, or whatever. We'll then iterate through the image views and create frame buffers for them. Okay, so let's iterate through them. For u32 I equals 0, I is less than swap chain image count and I plus plus. So for each of those, we create a VK image view, called attachment, and we're putting inside of it the swap chain image views. That's p app swap chain image views app position I. Grand. I think that's right. And then I'm just going to copy all this because there's a lot to type out. and we're just going to do that. So the render pass is also on our app, and the attachments aren't. It's here. Gotta call them attachments. Swap chain extent is on here, as is the extent, height, and width. Cool, and then we just do some error checking. So making sure that it's created. And if it's not created, we're probably going to exit with 10, because I think we did 9. Oops. Exit 9. We did indeed. Okay, and we're passing in p-app device, frame buffer, a null pointer, and the frame buffer's app position I to be populated by the create frame buffer function. Awesome. As you can see, at the end, as you can see, creation of frame buffers is quite straightforward. We first need to specify which render pass the frame buffer needs to be compatible. Okay, it's fine. Attachments, the attachment count and p attachment parameters specify the VK image view objects that should be bound to the respective attachment descriptions in the render pass. P attachment array. With the type parameters is self-explanatory. Come to the layout. Okay, it's fine. Our swap chain images are single images, so the number of layers is 1. I don't know what that means. Oh well. We should delete the frame buffers before the image views and render pass that they are based on, but only after we finish rendering. All right, and clean up. For U32 I equals to 0, I is less than swap chain frame buffers, Well, we know there's the same number of frame buffers as there are swap chain images. So p app swap chain image count I++ vk destroy frame buffer p app device, the frame buffer, which is going to be frame swap chain frame buffers at position I, and a null pointer. Same. All right, that's the cleanup all done. Let's just compile and check it all works. And it does. Excellent. Let's quickly move on, seeing as we're a bit ahead of schedule, onto command buffers. All right. Oh, bear with 2 seconds. All right, sorry about that. Quick intermission. Okay, command buffers. Commands in Vulkan, like drawing operations and memory transfers, are not executed directly using function calls. You have to record all the operations you want to perform in command buffer objects. The advantage of this is that when you are ready to tell Vulkan what we want it to do, all of the commands are submitted together, and Vulkan can more efficiently process the commands since all of them are available together. Same as we heard before. In addition, this allows command recording to happen in multiple threads if so desired. Oh, okay, that's very interesting. Command pools. We have to create command pools before we can create command buffers. Command pools manage the memory that is used to store the buffers, and command buffers are allocated from them. Okay, and a new class member to the store. All right. Let's go down here and create a new function call called create command pool. We call from within in a Vulkan. So we'll create our prototype real quick. Down here, and create next to frame buffer. Again, create frame buffer. Let's do it below here. Void app pointer to p app. Okie dokie, all set up. The command pool creation only takes 2 parameters. Oh, we've got to get our family queues again. Let's do that. I'll just scroll a little bit so you can see. Alright, the parameters are the pool info object, no doubt, and the p app physical device, and find queue families. Didn't we have that function somewhere? Oh yeah, but we also take in a surface as well. So, oops, p app. Well, that's not how you spell it. Surface. Alright, so I've got queue family indices, which I'm just going to call indices. I shouldn't have done that, should I? Indices graphics family dot value. That's just a regular index. 2 possible flags for command pools: the create transient bit and the create command buffer bit. Transient bit hint that command buffers are re-recorded with new commands very often, may change memory allocation behavior. Or the reset command buffer bit is allow command buffers to be recorded individually. Without this flag, they all have to be reset together. We'll be recording the command bit for every frame, so we want to be able to reset and recover from it over it, re-record over it. Thus, we need to use this one. Okay, command bit. Command buffers are executed by submitting them into one of the device queues, like the graphics and presentation queues we retrieved. Each command pool can only allocate command buffers that are submitted to on a single type of queue. Same kind of thing as the family queues we saw. Okay, we're going to record commands for drawing, which is why we've chosen to use the graphics queue. Fair enough. That kind of makes sense because that's what we're doing. Alright, let's just do this then. Whoops. Printf. Don't forget to null terminate. Exit with 11, I think. Okay, passing in a p app device, null, and the command pool. Okay, finish creating the command pool using the VK create command pool function, which is what we just did. It doesn't have any special parameters. Commands will be used throughout the program, so we will need to also destroy them. Clean up. Looks like we destroy them at the start. P app. Okay. Command buffer allocation. We now start allocating command buffers. Create a VK creator on our app. So much to do. Damn. Alright. We'll now start working on a create command buffer function and allocate a single command buffer from the command pool. Alright. So first we need to create our prototype, because that's the way we've been doing it the whole time. These are somewhat related so they can stay together. Create. Underneath here, we'll create a command buffer. Create command pool. And then underneath this function, we'll create our command pool buffer again. App, point to the p app. All right, and then command buffers are allocated with the VK allocate command buffer function, which takes a command buffer allocate info struct. All right, nothing special there. We've seen this plenty of times before. Let's just get this done. We're not really doing much in the way of thinking here. We're just basically going through the motion. P app, passing in the command pool and our device and our command buffer, and replacing that with printf, or printf, and an exit of 12. Yes. Right. All good. Level parameter specifies allocated command buffer. Where was that? Okay. Oh, okay. didn't type. So primary is going to be submitted to a queue for execution, but cannot be called from any other command buffers. Okay, and secondary is cannot be submitted directly, but can be called from primary command buffers. Okay, so it's like a hierarchical thing. Sort of. We won't make use of the secondary. Okay, fine. Since we are already allocated one command buffer, use the command buffer count parameter. Just one, okay. Command buffer recording now. So let's create a function. So we're going to the record function because this writes the commands we want to execute into the command buffer. The VK command buffer use will be passed to the as a parameter, as well as the index for the current swap chain image. Right, okay. So because that is being called from within one of these functions, I reckon we're just going to chuck it up here. Awesome. For us, this is actually a U32. There you go. We always begin recording a command buffer by calling the begin command buffer. And then, yep, the begin info struct. This all looks very familiar. Not a null pointer, just a straight up null. And then again, print F with our null terminator or mul and exit 13. Yep. Sorry, bear with again. And back. All right. So I did that. The flag parameter specifies how we're going to use the command buffer. The following values are available. One time submit, which is the command buffer of executed one time. Render pass continue. This is a secondary command buffer that will be, we're not using secondary command buffers. And use the simultaneous use. The command buffer can be resubmitted while it is also already pending execution. Okay, none of these flags are applicable to us right now. Okay, brilliant. The p inheritance info parameter is only relevant for secondary command buffers, so it's not us. It specifies which state of inheritance, which state to inherit from the calling primary command buffers. Sounds useful though. If the command buffer was already recorded once, then a call to VK begin command buffer will implicitly reset it. Okay, it's not possible to append commands to a buffer at a later time. Starting a render pass. Drawing starts by beginning the render pass with a VK command begin render pass. The function pass, the render pass is configured using some parameters. Yeah, same. All right, the render pass comes from p app again, as does the swap chain buffers. Oh, we haven't got p app, have we? Interesting. I guess we're gonna have to have that. Okay, app pointed to p app. So when we call our record command buffer, we have to remember to pass that in. Otherwise, we can't do some of these functions or create some of these structs more accurately. The first parameter we need is structure type. Obviously, we create a frame buffer for each swap chain image where it is specified as a color attachment. Thus, we need to bind the frame buffer for the swap chain image we want to draw to. Okay, using the image index parameter, which we pass in for every time we want to record, we can pick that right frame buffer for the current swap chain image. So I'm assuming we get the index of the image that we're playing with or using, and then we pass that to this record function, and then that passes it to create the correct frame buffer. That makes sense? Kind of. Clear as mud. The next two parameters define the size of the render area. The render area defines where shader loads and stores will take place. The pixels outside of the region will have undefined values. Okay, it should match the size of the attachment for best performance. Okay. Did I actually just copy that? Don't think I did. Wait. Come on, man. Why aren't you copying? What's going on here? Copy. Oh, whatever. Okay. Render area. It's going to be an offset. It's going to be 0 and 0. I'm assuming that's X and Y. It looks like we can't actually do that. Maybe we have to do X direct like this. Oh, because it's offset. X offset Y. Okay. And then render area extent. And this is going to be a p-app swap chain extent. Swap chain extent. Wonderful. The next two parameters, yep, okay, we kind of figure out what they are. And then we've got these. Why are you so obsessed with copying that? There you go. Some weird stuff happening in my clipboard there. Alright, the last two parameters define the clear values for the VK attachment load up clear, which we use as load operation for the color attachment. I define the clear color to simply be black with 100% opacity. Okay, so whenever we clear the surface, that's the window, it should just be black. Alright, cool. The render pass can now begin. Let's begin it. All of the functions that record commands can be recognized by the VK command prefix. Okay, they all return void, so there'll be no error handling until we finish the recording. Right. Okay, first parameter for every command is always the command buffer to record the command to. The second parameter specifies the details of the render path we've just provided. The final parameter controls how the drawing commands within the render path will be provided. It can have one of two values: the subpass contents inline or subpass contents secondary command buffer. First one is the render pass command will be embedded in the primary command buffer itself, and no secondary command buffers will be executed. Executed. The render pass command for the second one, the render pass command will be executed from secondary command buffers, but we're not doing that. And then we will not be using secondary command buffers. Yeah, I know. So there's our call, passing in the command buffer and the render pass info, and then the inline for the primary. Basic drawing commands. We can now bind the graphics pipeline. Exciting. The second parameter specifies the pipeline object. So what did we just do? Okay. Yep, so we've got the command buffer, the pipeline object, and we're using the graphics pipeline. Okay, that's fine. Which pipeline, which attachment to use as a fragment shader? Okay. P-app. As noted in the fixed functions chapter, we did specify viewport and scissors state for this pipeline to be dynamic. Okay. So we need to set them in the command buffer before issuing our draw command. Set them in the command buffer. Okay, I think it's still in the same function. Wow, look at all this. All right. So we don't do static cast, we actually just do regular old cast. And the swap chain extent is a p-app swap chain extent. Same again, regular float cast. And then we've got our command buffer and our viewport and our scissors again. Again, this looks like we have to do .x equal to 0 and same as y. There's our swap chain extent, and yeah, all right. Now we are ready to issue the draw command for the triangle. Oh, this is getting intense. Ooh. The actual VK draw command command v control function is a bit anticlimactic. Yay! But it's so simple because all of the information we supplied in advance. It has the following parameters aside from the command buffer: 3100 vertex count. So that's 3. Yeah, because it's triangle, 3 vertices. Even though they don't have a prefix, but okay, fine. Instance count is 1. Okay. Use for instance rendering for 1. Okay, that's fine. Vertex. The first vertex uses an offset for the vertex buffer defined by the lowest value of GL vertex index, which is 0. First instance is obviously index 0 as well. Okay. Finishing up, the render pass can now be ended. Okay, so we're recording the render pass and we have finished it. And we've finished recording the command buffer. Yeah, okay, so let's just do this. Printf and do our null terminator and exit with 14. Although I feel like it's probably the same kind of thing. All right. Okay, in the next chapter, we'll write the code for the main loop. But let's compile this and see what happens. It's good, works. Nothing breaks. We're definitely 100% definitely calling that function, aren't we? No, we're not. But we will in the next chapter. All right, so git add main.c and git commit created and recorded command buffer. Excellent. Git push origin main. And that is it for today. Next, we will jump into the joys of rendering a presentation, which should be pretty fun. Oh, it's a big one. Yeah. Till next time.